Hello, welcome to Fat Mama Physics. This is part 2 of Doppler Effect HL. This is specifically the derivations for the equation that we see here for the Doppler equation. In part 2, I'm going to derive this part of the equation, which has to do with the moving observer. So part 1, we derive the moving source. The moving observer, before we begin, I want to show us how this works in terms of the visual. Let's say I have a moving observer and I'm going to make sure my source is not moving. So here we go. So now I have a source that's emitting a constant frequency source. The wavefronts maintain constant distance, therefore constant wavelength. And here I have a microphone that's green, and it's every time you hear a bling, it's detecting the frequency, and how fast the blings occur dictate how the higher or lower the frequency. Now, if my observer is moving, then notice if I move this guy. Maybe if I move it faster. Okay, I'll do it again. The simulation doesn't catch up quite quickly, but visually, hopefully we can see that the microphone is going to see the wavefronts more frequently than if the observer wasn't moving at all. So that's if the observer is moving towards the source. Now, if you kind of see the microphone, I'm going to move this microphone away from the source. Now, I'm not really good at, moving the mouse as, making sure the observer maintains a constant velocity, moving away from the source. But hopefully we saw the visual where the microphone is, in a way, trying to run away from the wavefront that's trying to catch up to it. So before the next wavefront hits the observer, the perceived wavelength is now much longer. It took more time for the next wavefront to hit the observer. So because of the differences in the perceived wavefronts, therefore the wavelengths, the perceived would also be different, which then gives us a different perceived frequency. Do keep in mind the original speed of the wave that's in this medium is going to maintain constant, and that speed versus the speed of the source, the moving source versus the moving observer, are separate speeds. So I'm going to shut that off. I'm going to come back here. I'm going to try to do the best I can to draw this out for us to see. First off, I have a source, which I'm going to use in black. Is not moving, so I have a stationary source. The stationary source is going to emit wavefronts at a constant rate. I'm also going to have a person here, and this person, of course, is going to move, and I'm going to do the example where it's moving towards the source, and of course we just switch the signs if it's moving away or the observer's moving away from the source. Moving speed of Vs. So before we start, just to label some of the original source is moving with speed c, in which here we have the wavelength here. That's the original wavelength of the source. Also in the previous video, but again, I'll do it again as well. We know this is equal to the frequency of the source times the wavelength. And we also know from the previous derivation that the frequency is related to 1 over period, the inverse of the period. So this could be written as the frequency times the, divided by the period. And of course, if I want to write wavelength in terms of period and speed, I just cross multiply the period up. I get wavelength is equal to CT times period. So this guy over here, this is equal to speed of the wave in this medium times the period. Now, if my observer is moving, okay, so let's say that my observer detects a wavefront right here at this spot where I've drawn this person. And because, now this is where it gets a little tricky to visualize, but imagine that this black line here is moving towards the person, and then this person over here is also moving up to that wave front. That means that this, let's compare. If this observer was not moving, then this person's observed wavelength is just going to be this lambda. But because this person's moving forward, let's say by the time this person gets here, this person is then going to be able to detect the next wavefront earlier than they're supposed to. So let's say I'm going to draw this line here. So originally this black line was going to be here by the time this person heard it. But instead, it would only have traveled this shortened distance instead. So I'm going to draw this here, and this is kind of similar to the line of thinking we had earlier with the moving source instead. So I'm going to call this x. This x is going to be the distance traveled by the wavefront before the observer hits it and observes it. So in a sense, so this x is the distance traveled by the source of the wave. On the other hand, this distance here between the observer from where they first started, between where they've heard the first wavefront and the distance where they've heard the second wavefront, this new perceived wavefront, I'm going to label as lambda O. That's the observed wavefront the wavelength, because they first observed the first wavefront here. Then after they moved, let's say this is where the second wavefront hits them, they think that the wavefront is now shorter than, the wavelength is now shorter than before. So they will meet the next wavefront earlier, which makes their observed wavelength shorter. Shorter by how much? Well, this is going to be shorter by, well, to get that distance, first of all, this is based off of distance is speed times the time. So speed is going to be the speed of the observer. And hey, you're right. I made a mistake. This should be O. I'll put a red sign here so you know. This is the speed of the observer. That's going to move towards the source. And that's going to be VO, velocity of the observer, times the time it took for this person to get there. So then I'm also going to write instead, that time is period observed. So we can then also write this distance traveled by the wave of the source to be, this distance is going to be the speed of the wave in the medium, c, times the time it took to get here, which is this newly observed period. And really, that's just the time it took for this observer to hit the next wavefront because they're moving. Now, if we want to put all of this together, because in terms of distances, we can see how our observed wavelength, which is this part here, is going to be the entire wavelength between these two black lines. And that's going to be the original wavelength of the source minus this distance traveled by the source of the wave minus the x over here. It's kind of similar to what we did before. And if I have to write all of them in terms of, let's say, in terms of the speed of the wave and period, it's going to look like this. Over here for the observer, I have V times the observer times the period of the period observed. This is going to be equal to C, speed of the wave in the source, times the original period, and then minus the distance traveled by wave of the source, which is speed of the wave, times the period, the time it took the observer to meet the next wavefront. And just to remind us that, I'm going to write that there. So that T0 is the time it took the observer to meet the next wavefront. I wrote this one right over here. Because this is going to take a lot of space, or I've kind of ran out of space, or my pen's a little bit too big, too chubby, I'm going to rewrite this on a fresh page and finish the derivation for us here. So this is kind of where we left off. I will continue in green. That being said, it looks like we need to kind of isolate for some periods because they have a few, we have a few in common. So if I do that, I'm going to move one of those guys over to this side. That's going to be plus CT0 is equal to CT on this side. I'm going to put the T0s on the outside because we want to obtain the frequency instead of the period, of course. And we know frequency and period are linked together. So now that we have something that looks like this, we know from period is the inverse of frequency. So if I sub in frequency instead of period, I'm going to get 1 over the observed frequency times in brackets V0 plus C. And then on this side, I'm going to get period is going to be 1 over the original frequency of the source. And of course, we want to take the reciprocal of both sides because we want the frequency on top, similar to how we see it in the final form. And that's going to give us, I'm going to go up here because I think that's all the space I need. I'm going to get frequency observed divided by observer plus C. And just because adding order doesn't matter, later on I'm going to exchange the two just for the sake of, if I have a negative in front of V0, it becomes a little bit easier to observe, to see what's going on. On the other side, I'm going to flip frequency on top. This is technically the source, and I just keep forgetting to write source because originally it came from here. This is the period of the source, period of the source, period of the source, and it's all related to the source, okay? So this one over C, and then all we have to do next is we're going to cross multiply this guy up, which I'm going to get frequency of the source, frequency that it's observed. It's equal to the frequency of the source. I'm going to move that to the outside of the bracket. And then here I have swapping C and V0. I get C plus V0 over C, which this C is on the bottom, okay? And I get something looking like this, which is pretty close to what we have over here. Now, keep in mind that this plus was due to the observer moving towards the source. So it's positive because observer is moving towards the source. And therefore negative if the observer is moving away from the source. All of that is also summarized up here, which just says source. Moving positive. Oh, here, observer. Positive when moving towards the source and negative when moving away from the source. And going back to the point where I don't memorize these things, well, going back to this animation or this simulation here, we can see that if my observer is moving towards the source, then it's going to see the wavefronts more frequently. Frequency will increase. So moving towards means higher frequency. Well, the only thing, if I want this side of the equation to be bigger, observed frequency to be bigger, then in my numerator, I need a bigger number. The only way to do that is to add. So by adding the VO, I get a bigger numerator, therefore a larger observed frequency. Now, on the other hand, if my observer is moving away from the source, then they're going to see the wavefronts less frequently, meaning the frequency observed will be lower. To make the observed frequency lower, I need a smaller numerator. And the only way to get a smaller numerator is for us to subtract the VO instead of adding the VO. So again, I don't memorize plus or minus. I just go with what logically makes sense based off the theory. But anyways, this is showing the proof, or showing how we get the bottom or the other part of the equation for the Doppler effect. So essentially, we can see that the top part is if you have a moving observer, and the bottom part is if you have a moving source. Like I said again, on an IB style question, you will never see where both of them are moving at the same time, luckily. But otherwise, that concludes this video on derivations. Thank you for being patient with the entire process. Hopefully you found this video helpful. Good luck with your IB exams and studying. Family of Physics, signing out.